Good day, welcome to my first ever video on this YouTube channel, as well as the first video relating to mechanics. Today, I will be giving you an introduction to vectors. It is of paramount importance that you understand what a vector is and to be really comfortable with doing vector calculations, as it is a key concept that does show up in mechanics, physics, linear algebra, as well as various computer science modules. So starting off with the definition, a vector is something that has a magnitude and a direction. So when we talk about magnitude, we're talking about how much, right? So think of a car going 500, miles per hour. It's really quick, but that's how much it's going, right? If you think of the mass of a car, let's say it's 2 tons, we're thinking about how much. And when we talk about direction, we're speaking to the angle, right? So if you think of a rocket launching from Mars, at what angle is it coming to us? Is it launching from north? Is it launching from 25 degrees west of north? That is pretty much what we're talking about. So imagine that there's a field of grass somewhere here, and there's a football over here. And I kick this football, and it travels all along this way, and ends up right over here. I'll tell you that it started off at point A, moves to point B, and that's how you moved, let's say 7 meters, right? This in itself is not a vector. If we go back to the definition, a vector is something that has a magnitude and a direction. What does this 7 meters tell us? Does it tell us how much? Yes, it does. Does it give us a direction? No, it doesn't. So in order to make this thing here a vector, we would have to say 7 meters right. See, if I just tell you 7 meters, you don't know if that's 7 meters up, 7 meters down, 7 meters to the left, or 7 meters to the right. So in order for something to be a vector, it must have a magnitude over here, and it must have a direction over there. Now, if you've done physics before, you should know this. This video is more for students that haven't done physics. I just want to explain it from a very grade 10-ish perspective. So I hope that this is not too bad for you guys. So when we represent our vectors, we do it with a line and an arrow. So something like this. If you look at the length of this arrow, this is telling us the magnitude, also how much, right? And if we look at the direction of this arrowhead, it's telling us the angle, right? So together, they give us the magnitude and the angle. If you have a vector that's half the size, let's say something like this here, what we also know is that it's half in magnitude. So maybe it's going in the same direction. As you can see, these two things here are pointing both to the right, but one is significantly smaller than the other. So the size of the arrow will tell you which force is bigger or which vector is smaller, right? So just take note of that. You could get a question that might come up with a bigger vector and a smaller vector, and you'd have to be able to identify which one is larger and which one isn't. You can also represent your vectors on a Cartesian plane. So if you take this point here as 0, and let's say this point here is 10, and we go back to our football example where we kicked it, was it 7 meters? This is exactly how we'd represent it. Let's say I kicked it upwards for 9 meters. We would just represent it up on this Cartesian plane as 9 meters. So sometimes you'll see vectors out in the open, like we have on the left here. Sometimes we'll see them in a Cartesian plane. It's just very straightforward, very simple. So I've shown you how we represented vectors both on a Cartesian plane and graphically. Now I'm going to show you how we represent a vector in mathematical terms. So think of a vector, and we're going to call this vector A, right? We're going to say vector A has 2 components, A1 and A2. Now, A1 is your X component, and A2 is your Y component. So if you think of a Cartesian plane again, there's your X here, and here's your Y here. A lot of vectors aren't straight in the sense that they don't go in one direction here, or they don't go in one direction here. What we see with vectors is that they often go in funny directions, something like this, or something like this, or even something like that. And these type of vectors have both an x component and a y component. So that's how we'd represent them. So you can do obviously numerous calculations with vectors. The first one I'm going to show you is addition. So we have vector A here. Vector A has the components, let's say 2 and 3, and you have vector B, which has components 7 and 4. If you want to add A plus B, we start off by adding this here, and then we add this and this. So vector AB would be 2 plus 7 and 3 plus 4. And then obviously 2 plus 7 is 9, 3 plus 4 is 7. So that's kind of straightforward, vector addition. You then get vector subtraction. And how you do this is, so you have vector A, which is 2 and 4. And you have vector B, which is, let's say, 3 and minus 2, right? So don't be afraid of the negative here. Some vectors have negative components. Just get comfortable with that. So if I ask you what is A minus B, again, same as we did with addition, you're going to take these two components together, and we're going to take these two components together. And so what we'll end up with is 2 minus 3 as our first component, and then 4 minus 2. So a lot of people forget this minus sign here, and they just end up saying 4 minus 2, and that's not correct. It is 4 minus 2. I've seen this come up in tests before, and I've seen a lot of students lose marks because of this, so just take note. And then we get, well, 2 minus 3 is obviously minus 1, and then 4 minus 2 becomes 4 plus 2, because these two negatives cancel out, and then we end up with minus 1 and 6. So that is relatively straightforward, a little bit tricky with the subtraction, but still straightforward. I then want to do scalar multiplication. So that is when you have a vector, let's say A is equal to 7 and 4, and we have a scalar, and a scalar is just a number, right, of 7, and I want to find out what 7a is. Well, the way we work that out is that we put the 7 outside, and then you have your 7, 4, and then you just multiply out. So the 7 goes here, the 7 goes here, and then we'd get 49 and I think 28. Yeah. So that is pretty much the most basic computation that will come with a vector. You get your addition, you get your subtraction, and obviously you get your multiplication. The multiplication, again, you call it scalar multiplication. So everything we did here would be scalar multiplication, right? You also get a thing called a zero vector, which I just want to touch on. Zero vector over here, and that's basically a vector that has 0 and 0 here, right? So it doesn't move anywhere, it has no particular direction. It's pretty much a nothing vector, but it's something that you are required to know, so that's that. And then lastly, you have a thing called a unit vector. So if you think back to our Cartesian plane, it's just unit vector. We had a Cartesian plane like this, and I told you guys that we could represent vectors like this. A unit vector would be to scale this vector down so that this vector is just equal to 1. That is pretty much what a unit vector is, right? So let's say the magnitude of this here, right, the how much is 74, right? And I wanted to create a vector that has the same direction, but the magnitude is 1. How do you go about doing that? Well, first of all, you need to know how to calculate magnitude, right? So think of your normal vector as vector A, right? The way we represent magnitude is by these two lines over here, right? Let me draw that a bit better. So 2 lines, A. And I tell you that A has components 2 and 3, right? The way you're going to get the magnitude is that you're going to take the first component and you're going to square it, and then you're going to add the second component and then square it, and then you're going to take the square root. So you're going to end up with 4 plus 9 square root of 13, and this is your magnitude here, right? We'll do another example. So say you have a vector. It has a y component of, let's call it vector b, right? It has an x component of, let's say, 3, and a y component of 6, right? So the vector is going to look something like this. It's moving 3 units in the x direction, and it's moving 6 units in the y direction, so they can end up meeting somewhere there. So the vector is going to look something like this, right? I'm not drawn to scale, but it's going to look something like that. You know that this part here is 3. You know that this part here is 6. How do you get this magnitude? Well, what we basically doing is just Pythagoras theorem, right? So we're going to take our 3 square plus 6 square, put this under square root, we're going to end up with 9 plus 36, sorry, and then that's the square root of 45. That is your magnitude. So back to what I was originally talking about, your unit vector. All the unit vector is doing is taking this number here, the square root of 45, and we want to get it to 1. So the way you go about doing that is, if your original component, your original vector was 3 and 6, and they tell you that calculate the unit vector, you're going to start off, step 1 is get the magnitude, which is 45. Step 2 is to divide by magnitude, and it's that simple. So you take your components, so 3 and 6, and what you do is you put it over your magnitude, and that's it. That's how you get your unit vector. And what you find is that I'll probably teach you guys this in a couple of lessons. If you get the magnitude of each individually, they'd add up to 1. And that's it for today. This was my first ever video, and yeah, I don't have a lot of practice doing this, so I apologize if I wasn't good enough, but I'm gonna try and improve and hopefully make these videos a lot more better and a lot more informative. So I'd really appreciate if you guys could I'd really appreciate if you guys could subscribe to help the channel grow, as well as share this with your friends. And if there's anything, just leave a comment down below and I'll try to get to it. Thank you very much.